Hey everyone, if you're staring down a research methodology exam and feeling totally overwhelmed by the sheer number of definitions you've got to memorize, you are in exactly the right place. Welcome to this rapid-fire exam review explainer. We're going to organize, simplify, and completely conquer the 13 types of hypotheses you need to know. By chunking this information into easy-to-digest buckets, we'll lock these concepts into your memory so you can walk into test day with absolute confidence. Let's get started.
Here is our agenda for today's review guide. First, the hypothesis foundation. Second, null versus alternative. Third, simple versus complex. Fourth, substantiated, statistical, and practical. Fifth, positive and negative. And finally, sixth, universal versus existential.
All right, section 1, the hypothesis foundation.
So, what's a hypothesis, really? Well, simply put, it's a tentative solution to a problem. Think of it as an initial assumption based on, insufficient evidence that you haven't actually proven or disproven with hard data yet. In research methodology, we talk a lot about the inductive approach. That's basically working your way up from a problem, defining a clear, precise, and highly testable hypothesis, and then moving toward verifying facts so you can eventually build a solid theory. Your hypothesis, that is your absolutely crucial first stepping stone. Now, to make this study session actually stick in your brain, we're skipping the dry academic jargon. Instead, we're going to use one classic anchor example for the whole explainer, a father's adamant claim that eating ice cream causes his child to run a fever. For every new type of hypothesis we cover today, we'll run it straight through this exact scenario so you can see how it works in the real world.
Moving right along, section 2, null versus alternative.
You'll see this pairing on literally every methodology exam. They operate in total opposition to each other. On the left side, we've got the null hypothesis. This basically says, hey, there is absolutely no statistically significant relationship here. Any result you're seeing, it's just random chance. In our example, the child is essentially claiming the null hypothesis, saying that eating ice cream has zero relation to getting a fever, and if a fever happens, it's just a total coincidence. But on the right side, we have the alternative hypothesis. This is usually the exact thing the researcher is trying to prove. So the father argues the alternative hypothesis, claiming loudly that a relationship totally exists. Eating ice cream has a direct relation to the fever. And remember, if you accept the alternative, you automatically have to reject the null, and vice versa.
That brings us to section 3, simple versus complex.
A simple hypothesis keeps things super clean. You've got exactly one independent variable and one dependent variable. Eating ice cream leads to a temperature. Very straightforward, right? But as we all know, the real world is rarely that clean. And that brings us to the complex hypothesis, which deals with two or more independent variables interacting with two or more dependent variables. This is a brilliant way to see a complex hypothesis in action. Look at step 1. We don't just have ice cream. We have eating ice cream and being out in cold weather. That's two independent inputs. Now look at step 2. These combine to trigger two completely distinct dependent outcomes, running a temperature and absenteeism in school. It perfectly maps out all the moving parts of a complex claim. Next up, section 4, substantiated, statistical, and practical. Here, the absolute crucial point is knowing the exact distinction between these three. A substantiated hypothesis is incredibly general. It's just your expected relationship. We expect some kind of link between ice cream and catching a fever, but we aren't getting overly technical yet. A statistical hypothesis, though, that requires hard mathematical parameters. This is where you state that a statistically significant correlation exists, which you'll operationalize and prove using tools like t-tests or f-tests. You are looking for a definitive numerical link. And then finally, the practical hypothesis bypasses all that math and focuses purely on the real-world outcome. Who cares about the t-test if the practical reality is that eating the ice cream leads to the kid missing school? That real-world absenteeism is the practical outcome.
Section 5, positive and negative.
This pair is pretty straightforward, but you can definitely mix them up if you aren't paying close attention to the wording. A positive hypothesis focuses on a direct, affirmative result actually happening. Eating ice cream leads to fever. It's pointing straight toward a specific occurring event. The negative hypothesis, on the other hand, asserts a negative implication. So instead of saying what will happen, it focuses on the adverse side. Eating ice cream does not lead to good health. It's essentially looking at the exact same relationship, but filtering it through a negative exclusionary lens.
And our final grouping, section 6, universal versus existential.
This one is all about the scope and scale of your research claim. On the left side, the universal hypothesis is massive. It asserts that a relationship is true at all times for all variables. These are absolute, sweeping claims. On the right side, we have the existential hypothesis. This is much narrower and honestly a lot easier to prove. It states that the relationship exists for at least one particular case. Literally, it requires only a single instance of proof to be validated as true.
Let's lock this in with our examples. A universal hypothesis demands that eating ice cream in winter always leads to a temperature, for every single child, every single time. Good luck proving that, right? But the existential hypothesis is proven if eating ice cream leads to a temperature for at least one specific child. If even one kid gets sick, boom, it's validated. It's the same in a workplace scenario. A universal claim would be all employees will perform well if rewarded. But an existential claim recognizes human nature, stating at least one employee won't perform well despite the reward. Just one exception proves the existential claim.
As we wrap up this review guide, I want to plant a vital seed for your actual exam. Remember that when we take these 13 types of hypotheses and actually test them, we map them out onto a normal probability curve. Think about the father logging his child's temperatures. Most normal days, the temperature clusters right around the population mean, say 98.6 degrees. But when the child eats ice cream and spikes a fever of 100 degrees, that plot point deviates wildly from the mean. Here is the catch, though. As a researcher, you've got to watch out for confounding variables. Did the ice cream actually cause that 100-degree plot point? Or was it seasonal changes? Or maybe a mosquito bite? Those confounding variables can completely skew your data and make a null hypothesis look alternative.